Number 32. Compound A can be converted to either compound B or C. So two possible reactions. The energy diagrams for both processes are drawn on the graph below. And then up here we're asked several questions, A through F. And I've copied all of these questions down here one at a time, and we'll go through each of them. So let's go back and look at the graph here, the energy diagram. So what's going on here is you see two different curves. So you start with, at the beginning of the reaction, you start with chemical A, and at the end of the reaction, you can either end with B or you can end with C. So there are two different reactions. The blue curve, let me do this in the right color. The blue curve is A goes to B, and in the red curve, that would be A goes to C. So two possible chemical reactions. And the way you interpret energy diagrams is, the substances that you start with have to change into the substances that you end up with. The reaction coordinate means kind of like as time progresses, how does the energy of your substances change? You can think of energy as maybe structure of the molecule. So, as you start off with your reactant molecules, they become distorted and some bonds are broken. That costs energy. And as you start to form new bonds, you get the energy back. And sometimes, you can form something, or other times you can form something else. Anyway, there are two possible reactions that can occur here. So let's see what's asked of us using this energy diagram. So the first question, let me blow this up a little bit. First question is A, label each reaction as endothermic or exothermic. Endothermic is when the products have more energy than reactants. And exothermic is when the products have less energy than the reactants do. But when the products have more energy than the reactants do, that means, energy was absorbed. Okay, I'll put that here. Energy is absorbed. Because in order to get to products, they have higher energy than the reactants do. So the reactants must absorb energy to get over to the products. So let's see these two reactions. So look at the energy of the reactants, and then look at the energy of the two possible products. Well, it's this one right here has more energy than the reactants. So going from A to B, that's the endothermic reaction. So if you start with this much energy and you end with that much energy, then overall, energy was absorbed to get to products. So the endothermic one, let me color code this. So here, this will be A goes to B. And then the exothermic will be the other one. In exothermic reactions, products have less energy than the reactants do. And that energy that is lost, so if you start with a certain amount of energy in the reactants and the products have less energy, then what happens to that energy? Well, it's released. It's usually released in the form of heat. So you can see that's the profile here shown in red, an exothermic profile. A goes to C. And again, this is energy is released for exothermic reactions. All right, what is B asking of us? Which reaction is faster? Now, the faster reaction will have a smaller hill to get over. So when you're looking at the energy profile, in order for the reactants to convert into products, it has to get over a hill. Okay, you can think of that hill that is a barrier that represents some weird kind of change in the shape of the molecules, or maybe some difficult bonds need to be broken before new bonds are being formed. So as energy starts going up, this is hard to do. It costs energy, okay? But in the size of the hill dictates how fast the reaction is. The difference in energy between the reactants and the, the, the top of the hill, which is called the transition state, that's called the activation energy. Okay, so the idea here is the smaller the activation energy, that's the energy difference between what you start with and at the top of the hill. The smaller that activation energy, the smaller that barrier, the faster the reaction. So here are the barriers to get from, the beginning. So imagine this is how high the hill is if you're going from A to C. But look at how high the hill is if you're going from A to B. It's a taller hill, and it would be a slower reaction. It's harder to get over that hill than it is to get over this one. So I would call this one faster and that one slower. So A to C is faster. A to C is faster because it has a smaller activation energy. And then A to B would be slower because it has a larger activation energy. Okay, question C, which reaction generates the product lower in energy? Well, here are the two products. The products are either B or C. So you can see B has higher energy and C has lower energy, okay? So when you start with your reactants, if you're forming B, that's higher in energy than the reactants. If you're forming C, that's going to be lower in energy than the reactants. So here it's going to be A to C. Okay, that reaction generates products that are lower in energy than the reactants are. Question D, which points on the graphs correspond to the transition state? Now, what the transition state is it's the highest energy during the reaction. Okay, it's the energy it's at the top of the hill. It's the tipping point. Okay, that's what the transition state is. So when you're looking at these energy profiles, it's the top of the hill. It's the very tip of the barrier that you need to overcome. So if you're forming B, then the transition state would be this point up here. So E would be the transition state. And if you're going from A to C, then D is the transition state. Okay, what the transition state is it's kind of like what the molecules look like as they've become distorted, as much, the most distorted, like as they can possibly get before they start forming the new stable molecules. So the transition states are very unstable structures. So here are the two transition states, D and E. So I'll write D and E. Now, for E, label the energy of activation for each reaction. And we've already talked about this. The activation energy, this is the difference in the energy between the reactants in the transition states. So here, if you're going from A to C, then this distance right here, the energy difference between what you start with and the transition state, that's the activation energy for A to C. So this one right here, I'll color that a little bit differently. So let's color that in red. That would be the activation energy if you're going from A to C. And then from A to B, this would be the activation energy. It's the energy difference between what you start with and the transition state. And I'll color that one blue just to keep in line with the colors that we've been doing. So that would be the activation energy for A to B. The last one, F, label the delta H for each reaction. What the delta H is that this is the enthalpy change of the reaction, and this is going to be the difference in energy between the reactants and the products. Okay, so not between the reactants and the tipping point, it's going to be the energy difference between the reactants and the products. So here, if you're going from A to C, the difference isn't that great. Okay, so here I'll kind of indicate what the difference is. So this is, well, let me do it with an arrow. Okay, that's going to be the delta H for A to C. Okay, and what about A to B? Okay, it would be the difference in energy between the reactants and the products, and the products this time would be B. And so here I'll try and draw that. Okay, and that would be the delta H for A to B. So you see that going from A to C, the arrow points down. Okay, you're going to be losing energy here. The delta H, for A goes to C. It's going to be some negative value. I'll just put delta H is going to be less than 0. It's going to be exothermic. Okay, let's label this as exo, because the products have less energy than the reactants. Okay, and that energy is released. That energy that the products don't have must have been released. And then if you're going from A to B, you can see the products have more energy. Energy is absorbed to get from reactants to products. So that's an endothermic profile. So we'll label that one endo if you're going from A to B, and the delta H would be positive. So lots of information in this reaction profile, this energy diagram.